my lighting is not so good. Okay. For those who just joined in, please can fill up your attendance in the chat box. I have forwarded to you. Okay. So, all right. Okay, I'm seeing you guys are seeing. Okay. All right. I think we should start now. I was waiting for others to join in if there is any. Okay. So today we will continue about the fracture mechanics. Uh, that we have looked a little bit last lesson. Okay. Right. All right. Just a little bit of recap before we start. Okay. Let me cut this first. All right. So today I think we're just going to focus on this one, the stress concentration factor, right? And maybe next week we move on to Griffin's analysis. Okay. So right, a bit of recap. We have learned about the brittle and ductile fracture, and we have mentioned, or we have pointed out that the importance of ductile fracture uh, and the preference to ductile fracture compared to the brittle fracture, but somehow the brittle fracture still occur even in ductile materials under some circumstances, like shown here. And we have touched a little bit on the theoretical cohesive strength. Okay, and today I'm just going to repeat this before, because last time it was uh, a little bit of time constraint. All right. Okay. Okay, let's start here. Okay, so maybe not here. Just going to open one more page. All right. So you see that the atoms or the materials is made up from the arrangement of atoms. Okay, and especially in crystal. Okay, the arrangement, they are in orderly manner. Okay, so right. So when we are trying to figure out, okay, the right amount of energy to cause the fracture, okay, we have to start from the very fundamental scale, which is the atomic scale. Okay, the atomic scale. Of course, experimentally, we can just take a piece of metals or materials. We just set it on a tensile machine, and we just apply some tensile stress, and the material just fracture. Okay, it will brittle or ductile. Okay, it fracture, and we, based on the reading of the machine, we know the load, and we could get the strength or the stress, ultimate tensile stress, or the stress that is needed to cause plastic deformation, which is the yield stress. Yield stress. Oops. So that is on the macroscopic level, right? On the experimental level. So now we are going to dive in a little bit into the theoretical world, okay, where we start to look at things, or we evaluate, or we consider things at the atomic level. Okay, so to break to cause a fracture, okay, to cause a fracture, the atoms needs to be separated from each other. Okay, the atoms need to be separated from each other. So to separate this, okay, we need force. Okay, just like this. Okay, we need stress. Okay, we need stress to separate the atomic bonding. Okay, and as we have learned in I think in the very introductory of material science, that the atoms, they are hold together by a few mechanisms or a few type of bonds, right? And one of them, especially when we are talking about metals, okay, we are focusing on metals. They are bonded by what we call as metallic bonding. Okay, so each of the atoms, they are bonded to each other. They have attraction. We have this force that attracts them together. They don't crumble. Okay, they have this force that holds them together. Okay, so they are attracted to each other, right? And the attraction of the atoms, they have limitation. Okay, they don't attract until they become one, right? Because if you talk about attraction, it should be uh, closing up the gap. Okay, but how much they are closing the gap? Okay, so right, some light. Okay, all right. All right. So how much they are closing the gap? So there is limitation in that. This is also we have. I think we discussed this in the material science, very introductory of material science. So I'm just going to repeat this again. Uh, you see that two atoms where we consider two atoms. Okay, one is right here, another one is right here. Okay, so they have this attractive force. Okay, they have this attractive force. Okay, and as they become nearer and nearer and nearer, okay, the attraction is increasing. Okay, but at the same time, okay, there is also a repulsive force. Okay, they are attracted to each other, but please remember that they have the same charge, or at least each of the atom, okay, they have the electron cloud. Okay, they have their electron cloud, so they cannot uh, mm, become one. Okay, there are some limitation. Okay, because this is negatively charged, you cannot come that near, right? Because they have a different charge, same charge, so it will repulse. Okay, uh, right. So they are attracted, but at the same time they are experiencing a repulsive force. So it's a very complicated relation, right? They are attracted, but at the same time they repulsed it. Okay, so um, so what happened is that, okay, at a certain distance, okay, the atoms, they are they reach what you call as equilibrium state. Okay, meaning that the amount of attraction and the amount of repulsion is the same. So it is balanced right there. So they are like a short distance friend. I don't know. Okay, they are they cannot come so close, but they don't want to be too far. Okay, so they are something in the equilibrium distance. Okay, and this is what we call an interatomic spacing. Okay, there's a space between two atoms, interatomic spacing. Right. So uh, so this blue line, okay, uh, it give you the attractive force. Okay, so attractive force, we say it is a positive force. Okay, just put it that way because we need some direction for uh, let's say that going this way is going positive, going that way is going to be negative. So repulsive force always pushing. Okay, so it is a negative. The higher it get, the more negative it is. Okay, the higher the repulsion, the more negative it is. The higher the attraction, the more positive it is. So uh, all right, as we brings the atoms right here further from the equilibrium. Okay, equilibrium, the total is the same. Okay, this zero, the sum up of this force, they are zero. Okay, so um, as we bring this away, okay, the repulsion force, okay, the repulsion force, it decrease at higher rate than the attraction force. Okay, so when it is far, now it cannot repulse, or the repulsion force reduce faster. Okay, this one reduce faster than attraction. Okay, attraction also it is reduced. Okay, it also decrease, but at a slower rate. Okay, that is why when you exceed the equilibrium, okay, when you exceed the equilibrium, uh, the sum of the force would be in favor of the attractive force. Okay, because this one decrease at higher rate. Okay, uh right, if you, what happen if you go this way? Okay, this way, if you go to the left, the repulsion will become stronger than the attraction. Okay, attraction, the rate of the change of repulsion will be more, and the total of the force would be in a repulsive direction. Okay, so all right, so when you go, or when you want to break the bond, okay, you don't break the bond by pushing it closer. Okay, you break the bond by pulling it in the opposite direction, so you get the atoms, they are separated. Okay, so you pull it in the opposite direction, so they will be separated. Okay, um right, right. So eventually you will get this curve right here. Okay, eventually you get this green curve. Okay, this is the total force acting on the atoms. Okay, uh, right. uh okay, guys, so far, is it clear? All right, okay, that's good. All right, so All right. So now we want to break the bond. Okay. So one of the model that we or mechanism that we consider uh, in observing or in looking at the fracture, okay, is what we call a cleavage mechanism. Okay, cleavage mechanism. So a material is held together by strong atomic bonds. Consider a cleavage mechanism. How much stress must be added to break the bond? This is the cohesive strength. So cohesive, it is sticking up together. Okay, so the strength needed to break that sticking up together. Okay, to break that cohesiveness. Okay, right. So that is cohesive strength. So how do you get the cohesive strength? Um, right. From here, we know the relation between the force and the distance and the force. Okay, we know the relation between them. So we just copy and paste that into this graph right here. Okay, and this curve is difficult to be analyzed because we could not express it in a simple expression. Okay, so what do we do? Because this is a model. Okay, it's a model, so it does not necessarily to be the exact absolute truth. All right, it's a model. It's some suggestion, right? So what do we do is that we assign sine wave on this curve. Okay, you see that these broken lines right here is a sine wave. Okay, so we have, this is the exact curve. Okay, well, supposed to be exact curve, right? And we assigning a more assumption on this. Okay, uh, we are assigning it to be a sine function. Okay, although here it is diverted from its original curve. Okay, but sine function is easier to be expressed. Okay, so in sine function, I'm going to think going to all right. I'm going to maybe do some revision with you about sine function. Okay, okay, all right. So I think in high school, I don't know, in your matriculation maybe, because I have not gone to the matriculation. So sine function, you have y, you have x, you have this, right? It's very bad. Draw it one more time. Oh, it's still bad. But anyway, uh, hey guys, all right. Okay, sine function, it looks like this. Okay, it start with 0. Okay, and it ends with, or it come back to its original position at 2 pi, right? And the standard sine function, it has magnitude of 1, and here in the middle it has what you call as pi, right? Okay, so pi, sine pi equal to 0, sine 2 pi equal to 0, sine 0 equal to 0, sine pi over 2 will be equal to 1. Okay, fine. Sine 3 over 2 will be equal to minus 1. Okay, this is minus 1. Okay, this is the basic mathematics. Okay, uh, right. So this is what we call as the amplitude. Okay, if you want to express this, the standard, then it will be like this, right? So, okay. So we are going to derive this. We are going to convert this into something. For example, you have x and y. Instead of 1, we have, let's say, uh, a magnitude of 10. For example, okay. So your new, okay, this is, I'm going to put it away. Oh, this is too near. It's things that is the group. Okay, this is y equals sine x, right? And this is y equal 10 sine x. Okay, because the magnitude is 10. Okay, it's not 1 anymore. Okay, so this is also pi, right? So right. So if you change this from 10, uh, let's say, 'sigma c', okay, sigma c. This is just an amplitude, so you get sigma c sine x. So it is just a number, a value. Okay. Uh, okay, guys. Can you give me 5 minutes or 3 minutes? I have delivery. uh, wait, 2 minutes, 2 minutes. I going to take something. Okay. Okay, it's not Food Panda. It's not. Uh, it's GNT. Okay. All right. So we are back. Right. Okay. If we change the magnitude of the function, you just simply have to put it in front of the sign, right? So, all right. So in sine function also we have what we call as period, right? Yes, here the standard one, the period is going to be 2 pi. Okay. If you change that period, for example, okay, you change the period, let's say to 1 pi. Oh, this is also, I don't know what is wrong. Okay, I'm going to move this state, right? Should be around here. Okay, okay, x and y. All right, let's say that you uh, the period is not 2 pi. Okay, instead it is only 1 pi. Okay, just pi. Okay, in this case t equal to pi, right? So how do we write this function? We will write it as y equal sine 2x. Okay, so if we divide the t, okay, maybe we can simplify that. T equal to pi will give you sine x. Okay, t equal to pi, you simply going to have to divide the 2. Sorry, divide the 1 2. Okay, 1 divide the half. Okay, divide the half. Okay, so you get sine 2x. Okay, okay, so you divide the uh, multiplication of this. Okay, okay, boleh ya. This is, I think it's you have learned this before. I'm just boleh ya. So if your t, okay, become pi, your function is sine 2x instead of sine x. Okay. Okay. What if, okay, from here to here, what do? We multiply with half. Okay, we multiply with half. So the domain, what do we do to the domain? We divide with the half. Okay, so what if I want to put a just lambda? Okay, just lambda. You don't know, one lambda is just wavelength. Okay, all right. So what should I do if I want to convert 2 pi to lambda? So I would just 2 pi, I would just multiply it with lambda over 2 pi. So it will become lambda, right? Okay. So this multiplication need to be divided in the sine function. Okay. So you divide uh, lambda over 2 pi. Okay. So eventually you get sine uh, sine 2 pi x over lambda. All right. So here, what I'm showing you, okay, is we are having, okay, on top of that, on top of this, I want to multiply the amplitude to this value, or to this value. Yeah, yeah. So, so if I were to make a sine function, okay, draw in red. All right. Oh no. Okay. Anyway. All right. Now I want my sine function to be, to have an amplitude of sigma c, and the period of lambda. So what do I get? Okay, on top of that, I'm going to use the y here as sigma. Okay, just replace this y with sigma, that's all. Okay, it's a variable, and x as x. Okay, so right, so what function are we going to get is sine, oh sorry, sigma, because y we change to sigma, equal to sigma c, which is the amplitude, sine 2 pi x over lambda. Okay, so if we are looking at this uh, graph or this function, okay, all of you are agree, this one is this one. Okay, this is how we denote this one. Okay, all right. Okay, so we come back to our model. Okay, cohesive model. All right, so this line, okay, we assume it to be this one. Okay, just now. Okay, with the period of lambda and the amplitudes of sigma c. Okay, so we get the okay, this function. Okay, we get this function. All right. All right. So in mathematics also, for sine function, if the value is too little, okay, you can uh, write like this. Okay. Okay, you can write like this. Sine, uh, let's say a over b. Okay, if a over b is near to 0, okay, it is very small number. Okay, you can approximate it as a over b. Okay, you can try that with your calculator. Okay, it is an established mathematical rule. It's called small angle approximation. Maybe I forgot the name. Okay, but it is like that. The rule of mathematics is, if you have a small uh, number, if you have a small number inside the sine function, it is almost the same with the derivation or this fraction itself. Okay, so using this approach, we actually could simplify this into this. Okay, so now we have this one. Okay, sigma equal to sigma c 2 pi x over lambda. Okay, so right. Okay, okay, so all right. Okay, that's one part. Okay, that's one part. Okay, let's separate this. Okay, although you can see in the slide it is all together. I don't want to mess up your mind. Okay, this is one part. Okay, maybe just copy this. Look at the slide. This one. Okay, I'm just going to delete this. All right. Okay. Okay, now please do not look at this first. Okay. All right. Okay, now just now the story ends. Okay, just we look at part 2. All right. Okay, forget about the repulsion and stuff. Okay, we come to more simple approach. Okay, we have atoms. Okay, we have atom arranged like this, and when we apply some stress, some load, some force, right, it is stretched. Okay, it moved to, or it is displaced. Okay, displaced. Okay, this is the original interatomic spacing, and this is the displacement. Okay, so it's stretched. Okay, it is stretched. Okay, so the amount of the displacement is x. Okay, the amount of displacement is x. I think we have gone through this. Okay, in the material science, the stress would be equal to the Young modulus times the strain. Okay, and the strain is equal to the displacement over the original length. Okay, in this case original length is a naught. Okay, okay, so displacement over a naught is the strain. Okay, this is Hooke's law. Hooke's. Okay, the spring one. This is the same. Okay, with the atoms, you maybe you can go back and look at the SS curve. Okay, stress strain curve for elastic region. You find out this relation. Okay, so this one is going to be like this. If we write x over a naught. Okay, so agreed. Agreed. Okay, All right. Now we look at this part where we combine part one and part two. Okay. So part one, okay, part one, we have this. Okay. Let me copy this. This to here. All right. Okay, part one we have this, and part two we have this. So I'm going to rub this one off. Oh, right. Okay. Okay, the displacement right here is the displacement at the atomic scale. So it's all right. So X here we could strike it off. All right. And that leaves us with okay, let's leave us with this relation. Okay, this is okay, X sigma C equal to E over AO. The lambda now is on top. 2 pi is at the bottom. All right. All right. Okay. No mistake. Okay. All right. Or we can also like this. 2 pi. Also, no, not 2 pi. Go out of pi. Over pi. I think I'm sorry, you have to change a little bit in the PDF that I have given to you. Okay, the final answer you have to change a little bit. I'll tell you where. Okay, E over pi lambda. Oops. Lambda over 2. Okay. All right. Okay. All right. Okay. So this is what we have so far. Okay. This I'm just rearranging them. And all right. So shall we have a break or shall we continue all the way until we finish deriving this? Okay. All right. Okay. All right. So uh, okay, this is another assumption. Okay. So another assumption that we make here is that okay, this is the assumption lambda over 2 equal to a naught. Okay, lambda lambda over 2 is equal to a naught. So you can strike this off. Okay, so well, I think it's reasonable. It's written in the book as reasonable. Okay, but the explanation is a bit lag, but we can consider it. Right. Let Let us discuss about this. Right. Okay. So we are looking at the two atoms. Okay. Okay. Let's. Okay, we are looking at two atoms. Now we want to assume, okay, we want to assume to simplify our expression, we want to assume that lambda over 2 equal to a naught. This is what we want to assume. Lambda over 2 is equal to a naught. Okay. Okay, once it become like this, then our equation just now would be just, okay, sigma c e I lambda over 2, and sorry, not lambda over 2. Lambda over 2 is equal to a naught, so that would give us this as a naught. Okay, a naught n times a naught. So we can strike this off, so it becomes e over pi. Okay. Okay, this is what under this one. Okay. Right. So how come we got this assumption of lambda over 2 is equal to a naught? Okay. That is the assumption not made by me, okay? By the scientists before, okay? They, okay, claim that, okay, it is reasonable. Why? Okay, we look at these two atoms. Okay, so you see interatomic spacing. This is a naught. Okay, this is a naught. Okay, this is a naught, where it is in equilibrium. Okay, so when you stretch, okay, when you reach this lambda over 2, okay, the force, okay, the bond, okay, it's almost zero. Okay, it almost no effect. Okay, in it could have small effect, but it is based on our approach from the sign. Okay, the whole almost no effect. Okay, so we are assuming, okay, that, okay, this is interatomic space is a naught, right? So meaning that we are considering the metal, okay, metal. So it is atom, okay. So meaning that the size of atom is also like this, okay. This is from center to center. If we are talking about ion, maybe it is different, okay. The size of radius is different, but now we are talking about metal, so the size of atom, they are the same, right? So all right, when, okay, so the size of atoms is a naught, okay, or the diameter of atom is a naught. So when it is far from one another, okay, as far as the interatomic spacing, okay, as far as the interatomic spacing, so at this time, at this point, okay, the uh, bond, okay, the strength is almost becoming null. Okay, so that is why we make this kind of assumption. It is reasonable. Okay, when you are near, okay, you are having this attraction. Okay, this force. When you are a bit far, now you have no or almost no influence. Okay, and how far? Okay, the assumption is to be around lambda over 2. Okay, around lambda over 2. Okay, lambda over 2, sorry, the assumption is to be around 1 atomic distance. Okay, that is from minimum to maximum to minimum again, that is lambda over 2. Okay, so this distance, okay, this distance of from a relaxed to a very high strength, okay, to move it and then go less strength again. Okay, this distance, okay, is assumed to be, or is taken to be uh, the same length as the interatomic space. Okay, that's the assumption. Okay, okay, so that is where we get this a very simple uh, one. Okay, so in your, I think in your PDF with you, so I'm telling you, please correct, do correction. I think in your PDF it say that lambda is equal to this one. Yeah ke? So in the end you get this one is equal to E over 2 pi. So please change that to this one, okay? Because this is more known. Okay, maybe some book right 2 pi, but as far as our reference concern, okay, this is the right value. Okay, all right. This all right. Okay, so let's have a break, guys. 10-minute breaks. Uh, all right. So we start again at 12:13. Let's make it 12:15 lah. Okay, 12:15. Okay, guys, welcome back. All right. So just now we have looked at the cohesive strength. Cohesive strength. Okay, theoretical cohesive strength. Okay. Right. Pick up where we left. All right. So, based on our calculation just now, okay, we have sigma c equal to E over 2 pi. Okay, this is what we get from our calculation or our derivation just now. Okay, all right. So if we look at this materials properties, okay, we pick up one, for example, cast iron. Okay, we pick up cast iron. So cast iron, the Young modulus, okay, the E that we calculated just now, okay, the E, all right, is 67 gigapascal, okay, 67 gigapascal. So therefore, the cohesive strength, I think this is not the right value, okay, because it is using the divide by pi, but indeed it's 2 pi, so you just need to divide again by 2, so it's 5.325, 5.325. Okay, so 5 gigapascal, okay, 5 gigapascal is around uh 5,000 megapascal. Okay, 5,000 megapascal. But times 2 mana tadi, saya pun dah pening. uh, Macam mana yang silap tu, yang first tu? uh, Dia macam ni pi kan. So kita ada E, okay, kita ada E, kita bahagi dengan silap yelah silap, itu pi tu salah. Okay. Upside, terbalik. Not this one. Okay, so kita darab dengan 2 lah. We multiply by 2. Yeah, you're right. This is not the right one. Okay, I was thinking this one again. So just divide by pi. So you times 2 lah. So it's around 20 gig. Komputer pula 20 gig. Alright, so around 20 gigapascal. So 20 gigapascal is around 20,000 megapascal. Okay, but when you look at this experimental value, okay, you find out that the strength does not reach to that extent. Okay, it is extremely low compared to that. Okay, it's only 600 megapascal, 669. Okay, or yep. So there must be an explanation to why it is very low. Okay, why it is very low. So all right. So when we were talking about theoretical, okay, we are taking things into perfection. Okay, there's no flaws, right? But in reality, okay, the situation is not always like that. Okay, in materials, there will be, of course, there will be flaws. There will be some inclusion from other materials. There will be pores. There will be vacancy. Okay, there will be defects, right? So this actually degrades what the theoretical strength uh, was, okay, or is, okay. So look at this video made by Dr. Viba, okay. It's a very interesting one. So you take one piece of paper, you try to stretch it. Maybe it's difficult, but when you do this, okay, when you put some notch, okay, it breaks easily. Okay, right. So uh why? Because there is stress concentrated. Okay, because the stress is not always uniform. Okay, the stress is not always uniform. The measured fracture strength for most materials are significantly lower than those predicted by theoretical calculation based on atomic bonding energy. This is what we comprehend just now. We have learned about this. Okay? This discrepancy is explained by the presence of microscopic flaws or cracks that always exist under normal condition at the surface or inside the material. So there will be flaws, cracks, okay, across the material. So it is almost impossible to get a very perfect materials. That's why the strength, okay, the yield strength or the ultimate tensile strength is lower than what we have uh, calculated or derived from cohesive theory. Uh, this is a simulation, okay, a crack 0.75. Okay, you see that this is a crack, although it's not that obvious. Let me zoom in. All right. So this is the crack. The crack. This crack. Okay, crack. 0.75 long under monochromatic light. Okay, not simulation. This is under monochromatic light. So you can see the berlawan. Okay. So you see that here is, it has a longer one, longer crack. Okay, and this 7.25, okay, is much more longer. So when you do simulation, okay, simulation, it looks like this. So it is concentrated, okay, this area, right? How much, okay, to visualize that, okay, to visualize that, okay, for example, okay, there are maybe two condition, one see two situation. On one, maybe the crack is at the edge, okay, and one is at the center. Okay, so this crack tip, okay, crack tip, this is crack, this is the tip, okay, the tip, okay, you have a crack, for example, you have material, you have a crack, okay, this is the tip, okay, the crack tip has the highest stress, okay. As you go further away from this crack tip, okay, you get nominal stress again. All right. So it could be not on the edge, maybe at the center. Okay, the crack tip, it has very high stress. As you go away from the crack, maybe you get lower stress, which is equal to the nominal stress. But doubtly to uh, maybe you have another crack. Okay, maybe you have another void. Yeah, after that. Okay, so well, ideally it looks like this. Okay, it looks like this. So the crack tip has the highest stress. Okay, the highest stress, and as you go away from the crack, okay, your stress would approach the nominal stress. Nominal stress is this one, you apply. Okay, not concentrated one. Okay, all right. Okay, so this is how it looks like when you do simulation. Okay, you find that the crack tips is concentrating, the stress is concentrated at the tip, and this what this guy English, okay, come up with. He quantified it or expressed it in a equation, okay, where it's called stress concentration factor. Okay, stress concentration factor, KT. Okay, what is T? I'm not sure. Okay, but stress concentration factor, KT, right? Right. Maybe tip. Okay, maybe tip. I'm not sure. Okay, by analyzing a plate containing an elliptical hole. Okay, this is ellipse. Okay, ellipse. Okay, the shape, ellipse. Okay, this elliptical hole, English, this guy was able to show that the stress concentration factor KT is equal to 1 plus 2 A over B. Okay, 1 plus 2 A over B. So this is what English come up with. Okay, right. So what is meant by stress concentration factor? Okay, it just simply means, if you look at this graph back, okay, this maximum, okay, the maximum over the normal, the nominal one. Okay, how what is the value of that? Okay, what is the value of the multiplication? Okay, that is what is meant by stress concentration factor. So if you want the max, okay, you just simply need to multiply the nominal with the factor. Okay, if you know the factor, you multiply the nominal stress that you apply to the stress concentration factor, you get the stress at the tip. Okay, and it is given by this by English. Okay, English. KT simply a measure of degree to which an external stress is amplified at the tip of a crack. Right? So 1 plus 2A over B. So just remember this, okay? All right. Rearranging one, okay? This one, equation number one. Okay, like I just show you here. Okay, rearranging it, you get something like this. Okay, just bring that sigma naught up, and then you get this one. Okay, rearranging one, we can predict sigma max at the crack tip. Sigma max equal blah blah blah. Stress is predicted to go to infinity as the ellipse flatten to form a crack. So if B, this B, okay, if it is getting smaller and smaller and smaller, like a crack, okay, uh, the stress would become infinity. Okay, if it is not approaching zero, maybe some value, you can still calculate it. Okay, all right. This is based on the geometry. If you know, maybe if you want to have this one, maybe you can Google ellipse. Ellipse. Google ellipse in the Wikipedia. You get this relation of the shape, and just simply the geometrical relation. Okay. Uh, the curvature rho at the tip of an ellipse is related to its length and width by b square over a. Okay. Solving this for b and substituting it into equation 2 in previous slide give us this one. Okay, so just simply they say that okay, we don't want to put b here in this equation. Okay, we don't want to put b there. Okay, just want to put curvature and a. Okay, so what you do, you just make it rho over a root. Okay, so this is b, so you put there b, and now we are happy. Okay, we got this one. Okay, so this form. So right, the equation shows the large effect of notch radius. Okay, why? It is not simply because we are happy to do so. Okay, just want to demonstrate. Okay, the radius or the notch. Okay, the notch radius, the sharper the notch means the smaller the row. Okay, the larger the stress concentration factor Kt. Okay, thus sigma max also become larger. Okay, all right. Okay, so when this is large, when this is small, when this is small, okay, and you further you root it, it is already small. Okay, you root it, it will be extremely small, and it is denominator. So when you divide it, it will become very become very big. Okay. Um, right. When B becoming really small, the crack. Okay. Crack usually B is very small. Okay. A now become significantly bigger than rho. Okay. Equation 2 reduces to like this. Okay. Why? Because now we are just ignoring this one, because this is big. Okay. All right. So Kt, well, this is the same. Okay, equal to this one. Okay. So A over curvature, you root it to. So this is for very small b, which is the crack. Okay. So stress concentration factor is now reduced to this equation. Okay. So the first one looks more complicated, right? Now it looks like this. Okay. It is also complicated. Okay. So English elliptical result in result 2 in equation 2 reduces to sigma max equal to 3 sigma naught for special case of a hole where A equal to B. So when A equal to B, okay, what happened? Rho is equal to A. Okay, A equal to B equal to A square. You strike off the A, you got rho equal to A. So rho equal to A, this is A. So A over A become 1. You square root 1, you get 1. You plus, you times 2, you plus 1, you get 3. Okay, 3 sigma, sigma naught. So this is special case lah, right? Uh, Example number 1. Assuming a microscopic sharp hole, a microscopic sharp hole of a length A equal to 10 to the power of minus negative 1, which is 1 micron, and the radius, the rho there, okay, at the tip is 3.3 times. Okay, there is answer already. Okay, or you can try it by yourself. Maybe just key in Excel or whatever calculator if you have. Okay, you get the answer of 115. See that the stress concentration is very, very high, 115 times. Right. So that is why okay, if an applied stress of 120 megapascal is applied to a plate of cast iron containing this crack, will it survive? Stress, okay, nominal stress is 120, okay, but you see stress concentration will be 115, or well, just okay, okay, that is okay, sorry, okay, 115 megapascal, okay, which is very large, that it exceed the cohesive strength. Okay, just now we, if you still remember here, we say that, oh, okay, we have calculated the cohesive strength. Okay, cohesive strength is very high, right? Because we have this formula. Okay, you use the Young modulus. Okay, you use the Young modulus, you have a, I don't know how much, it's 20,000 something, right? Okay, 20,000 megapascal something, right? So how can the material break? You have a very high cohesive strength. Okay, so, and then we just, you know, talk about, oh, maybe there will be crack and stuff, right? And when we put that into our calculation, right? So the apparently we apply 120 megapascal of nominal stress, but locally, okay, when you observe at the tip of the crack, okay, at the tip of the crack, the stress there is not 120 megapascal, but it needs to be multiplied by the stress concentration factor, Kt. Okay, so when you apply that to this value 115, so you got a very large number of stress, okay, that is comparable or exceeding the cohesive strength. Okay, another example. Okay, before, I think we're going to end before this slide around, yep. Right, because if I go, then it won't be enough time to go. All right, all right. Example number 2, what is the magnitude of maximum stress that exists at the tip of internal crack having radius? So I should have deleted this earlier. Okay. What is the magnitude of the maximum stress that exists at the tip of an internal crack having a radius curvature of 2.5 and a crack length of 2.5 when a tensor stress of 170 megapascal is applied? Okay, what do we do, guys? You use this equation. Okay, so you apply the stress 170. Okay, just put it there. We have already looked at it. Okay, so our applied stress 170 megapascal. Everything in megapascal. Just put it. So two. Okay, the square root of A. A is the length. Crack length 2.5 times 2 megapascal, so it should be in meter. So this is like this, right? And no, it is square, is it? Oh no, not square, it's just the length. The length you need to divide with the 2.5 times 10. Okay, so this one is just cross each other. Just cross this one, you get the round 10 22 kat bawah 100 ya. 100 punca di 10 10 20 120 20 ya. Is it true? Is it, did I miss something in my calculation? 100 bawah ni 10 20 20 140 let me calculate that. 20. Oh, something is wrong. I don't know where. Correct length. Maybe the answer is 3. 3, 3, 4. I think 3. Anyone get the 2? This should be strike off, strike off. Strike off, strike off. This is yes. I also got 3, 4. Maybe the slide is wrong. The slide is wrong. Yep. So if you just use the formula, you get the answer lah. Okay. Alright. Alright. For brittle material at certain length of initial flow and the applied load, failure will begin at the point of stress concentration. Essentially, a crack begins to form at this point, and a higher stress concentration will develop at the tip of this crack. Thus, in turn, causes the crack to propagate over cross section, resulting in sudden fracture. So, okay, before we end this, okay, I think this statement is important to go to the next episode, right? All right. First we derive theoretically the cohesive strength. We find out that the strength is very high, very high. And what did we do after that? We think that, oh, maybe there's flaws. So we put flaws into the ring. Okay, we observe it. Okay, we identify that there is a stress concentration factor, which would multiply your nominal stress that you applied to a very high number that is comparable to the cohesive strength. That is why your your experimental yield strength UTS somehow is not that high. Okay, so right. So now, okay. Imagine if the crack is really small. It's really small. KT will be nearing the or approaching infinity. Okay, in that case, KT would approach infinity because it's very small. Okay, which will lead to sigma x, sigma max approaching infinity as well, which will always lead to crack propagation. But that is not the case. Okay, that is not the case. Okay, if we consider the 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 crack, the crack, if we say that if it is small, then KT will be very high. Okay, because according to the equation, right? Uh, it's B, yeah, B. If we have B, let's see, yeah, B. I think it's more easy to understand if you look at this. Okay. Okay, if B is very small, your rho is very small. Okay, very very small. Okay, this now it has gap, right? You have to be. It looks there is. What if this approaching just one line? Okay, very small. Okay, so this one would be very very small, and this will give you a very big approaching infinity of KT. And when KT is approaching infinity, sigma max also will approach infinity. Right, and that would lead us to always crack. Okay, so whatever if we have a small defect only, and then we apply the stress, cracks. Okay, it seems to be like that if we just follow blindly the uh, equation, right? But that is not the case. Okay, thus we must come up with different framework to understand the relationship between applied load, the local stress concentration, and when a crack becomes stable in a structure. So the crack might be stable